Okay, so as Karina said, this is a 101 course or talk in high-performance computing and high-performance data. High-performance computing and data, these are tools that we use at GA, and they're becoming increasingly important. And I just wanted to start with this. They are important to GA in allowing us to meet our science principles, primarily in that these are going to be how we can do quality science. But as we start talking about the data, we'll see that this also helps us in doing collaborative science and transparent science. Now, the talk today, here's the presentation. We're going to split it into two. I'll talk about high-performance computing. Alex will talk about high-performance data. I'll be going through the basic concepts of computing. This is 101. Hopefully, I'll be able to explain a lot of the jargon that people hear and may or may not understand. I'll talk about the different types of high-performance computing. That's what the HPC stands for. And then after that, I'll go into a little bit about the National Computational Infrastructure, the NCI, and how Geoscience Australia uses it, and then how people can actually become users of the NCI. Alex will follow a somewhat different format. He'll go through what is high-performance computing data requirements, so how do we use data, what data formats are, how this helps us in high-performance data, and then talking about the fair data principles. So we'll start off just by saying what high-performance computing is, and this is an interesting one because it's a different thing for different people. And there's a technical and a common usage. For many people, high-performance computing just means anything that you can't do on your desktop, right? So in order to solve large problems. But when we start getting to a technical level and we start talking about high-performance computing centers and supercomputers, there's a slightly different definition, and this is where we start talking about parallel processing techniques to solve complex computational problems, and then systems that allow us to do more than 10 to the 12th floating point operations per second. Now, we're already into jargon. I'll step back, I'll go through some of the basic concepts, we'll talk about what these different terms mean, the importance of parallel processing and floating point operations, et cetera, et cetera. So to start off, I don't know how many people have actually looked inside of a computer. Is there anyone here who's never looked inside of a computer? Okay, pretty much everyone here has looked inside of a computer. Now when you look inside of a computer, and this used to be fun, I used to teach programming, so this was the first class, was always to pull a computer apart. Key things that you think of is you've got a power supply. This is the bit that plugs into the back of into the wall. Never open this up while it's plugged in. We've got our hard drive, which is where we store the memory. We've got a whole bunch of expansion slots. We've got a whole bunch of connections. They may be floppy drives. They may be CD-ROMs, all these types of things. And then we've got this thing called the motherboard. The motherboard, which is located in the middle there. I unfortunately don't have a pointer, but I guess I can. So the motherboard's located right here. This is a circuit board, and it's really the brains of the computer. This is where all of the processors are and all of the calculations and operations are performed. So CPU, this is our first term, if we exclude motherboard. This is the central processing unit, and you can think of this as the brain of the computer. It has has several processors that can be on this unit, and these are processing cores, and we can have multiple cores. So that means that in a single unit, we can have multiple cores and therefore do multiple operations. So if you start hearing, everyone likes, well, not everybody, but the IT guys like to compare how big their computers are. This used to be a thing. We have things like quad cores and dual cores and all that. That tells you how many cores the processing unit has. Okay, so quad core is 4. We'll go a little bit further in that later. Now RAM, this is also part of the memory board. This is the memory that actually works with the processors. This is what we call volatile memory. It's where the operating system will reside, the application programs and data, all the things that you're currently using. And this is going to be the fastest speed communications. It'll interface directly with the processor. So the RAM's really important for when you start processing. Now, we've got two main types of processors. We have the CPUs that I already talked about, and we have something else called GPUs. GPUs, that's graphics processing unit. This is something that has come about more recently, and it's optimized for handling graphics manipulation and calculations. And if you want to get a good GPU system or a graphics card, you go for whatever the gaming industry is using, because this is where the advances are being driven. Now, architecturally, they're different than the CPUs. CPUs tend to have a limited number of cores and lots of cache memory, so memory that can be used for storing data and things like that. And it can only handle a relatively few number of threads at a time. In this context, when we talk about threads, this is the number of tasks that can be run simultaneously, right? So if there's 2 per CPU core, if you've got a quad core, you multiply that by 2, you get 8 threads, 8 things you can do at one time. Now, in contrast, a GPU, these can have hundreds of cores on the single unit. You can process thousands of threads, and because you can do so many things simultaneously, this can really speed up your software. And in addition to speeding up your software, so how quickly it will run, it also ends up using much less energy, right? So there's a lot of movement toward using GPUs because of this. However, there are some downsides to GPUs. CPUs are standardized. That means that if you write software, if you have an application that will run on CPUs, you can use it on pretty much any system that has CPUs. GPUs, because of their design, you have to rewrite the software. It has to be able to run on that particular GPU system. So CPUs, definitely an advantage, but GPUs have advantages too. Now, so far I've been talking about single units. Single units are pretty much limited in how many calculations, how much work we can do at one time. When we want to start doing lots and lots of things, we have to start moving beyond single machines and single units. So when we talk about performance, this is how quickly, so what the calculation speed is. This is measured in flops. Flops, floating point operations per second, and that's just mathematical operations. So if we want to speed these things up, we can either do it by increasing the processor speed, so how quickly an individual calculation can be made, or we can increase the number of processors, right? So we can see this is something called Moore's Law. You may have seen this diagram before. Moore's Law basically predicts that we'll double the processing performance every year, and you end up with this sort of curve. So flops, we can increase the processing speed, but also we can increase the number of units. And so commonly when we start combining units, we call these things nodes. So a node would be a single machine or a single board housing a CPU, and then each one of these nodes would have shared memory and connections, etc. So the other thing that we'll get into later on, because this is really going to be an important thing, is that although we're getting faster and faster machines, we can do more and more calculations, the memory performance is not increasing as quickly. Memory is starting to become a real problem, and when we talk about memory performance, it's the speed at which we can actually read memory or write memory. So transferring it, moving it from wherever it's being stored to wherever we're doing the processing. So if you've ever been to one of the NCI talks here at GA before, you'll probably have seen this, this picture. It's a way that we sort of show the increase in performance in time. That red line in the middle, that's the fastest, the #1 machine in the world. And you can see that we've got 10 to the 7th gigaflops, so that's petaflops now. And NCI, this is a slightly old graph. I couldn't get a newer one. The NCI in 2017, so the National Computational Infrastructure here in Canberra, is sitting about 1.7 petaflops. And so here we have the line for number 1. It extends up, and we're sitting around number 70 in the world with that facility. But it's just continuously improving. So supercomputers, that's what the NCI is. We've got a whole range of different types of computers, and depending on what you're trying to do, you can use all of these different systems. And so we've talked a lot about, you hear a lot about these things just to sort of explain the difference. Desktop computers, everyone at GA probably has a desktop computer or a workstation. These are becoming more and more commonly. They're multi-cored, and the bigger machines will have up to 8 cores. Okay? They have installed operating systems, and most people at GA will have a Windows machine, but you may have something else like a Linux machine, or you may be a Mac OS operating system person. Now, with the recent ICT work, we've been moving to cloud. And when we talk about cloud, GA is primarily using Amazon Web Services, or AWS. And there are a number of different cloud providers. Most often when we talk about using these cloud providers, we're talking about using a single instance. And instances are the equivalent of a single node. So again, we're talking about a single processing unit. And these things range from about 1 processors up to 128. So that's much bigger than what you can do on your desktop, right? They come with different memory options. The downside to these is that they're typically self-service. That means if you just go to AWS and you get an instance, they can be quite inexpensive, but you have to do some work to actually use it because it doesn't have an operating system, it doesn't have a security and all these other things that you would need in order to use it to run your software or your applications. Now, when we get to the multiple machines, so we want to go beyond 128 cores, or we just like the idea of having multiple machines, we start talking about clusters. And GA has a number of different clusters. This is where we link nodes together and they increase the computing power. Okay, typically these will have some sort of operating system on top of them. You can say this is platform as a service. They've got an operating system, security, etc. And so you can actually stick your applications on the cluster if it's set up that way. Now, beyond what we have at GA, it's possible to use cloud clusters. So these are things that would come from a cloud provider, and it may be as simple as combining different single instances. Again, this is going to have the problem where you're going to have someone who knows what they're doing, and they'll have to build all the different systems, put in an operating system, etc. And actually, people are using cloud clusters to do true high-performance computing. There are examples of people using thousands of nodes in the cloud. Okay? You can also get this as a service, so people provide operating systems, etc. Then finally, we get to the supercomputers. And this is where we talk about the NCI. With supercomputers, you have a single machine, and you have thousands to 10,000s of co-located nodes. So lots and lots of processors. They're controlled by a single operating system, and they are optimized to perform lots and lots of calculation every second. Now, one of the downsides to these types of systems is that you have to submit your jobs in a queue, which means you don't get to run your job at that time. We'll talk a little bit about that later. Okay, so that's what computers are. We have these increasingly bigger computers with different processors, but to take advantage of all those extra processors, you have to actually design your software, your applications, to accommodate that. So this is where we start talking about parallel programming. Parallel programming just means that the software is designed so that it can do multiple operations or processes simultaneously. Now, if it's designed really well, you can do lots and lots and lots of operations simultaneously. And so the software that we tend to run, or someone writes to run on their desktop, won't necessarily work very well on a supercomputer because it may not be designed in a parallel fashion. Now, to see how well something is parallelized or how efficient it is in a supercomputer, you can do something which is called profiling, and that allows you to see how the speed of the program, how the speed up goes as you increase the number of processors that you use. Now, this is a theoretical curve, and all it says is that if a code or a program is 50% of the program is parallel, then it speeds up as you increase the number of processors, but you get to a certain point where it's never going to speed up. So you can take this software over to a supercomputer, but there's no advantage to using more processors because it's still going to take the same amount of time to run. Conversely, if you have something that's very well parallelized, so this one's 95% is parallel, you can speed it up and speed it up, but even then you'll still hit some point where you stop getting speed ups, right? So one of the reasons for this has to do with input and output, so I/O. A big portion of any sort of software application is just transferring data from memory to the software so you can run the operations, or writing it back. And this is very difficult to parallelize, and so this ends up being one of the main blockers to actually getting really good parallelization. Okay, and then these other terms that we get to when we talk about high-performance computing systems, we have the queue. That's just this network. There's a scheduler on the system that says, okay, this person wants to run a job. I'll put it into the queue, and based upon how many different processors it wants to use, it will schedule and start the job in some way so it can efficiently use the whole machine. So it may take you anywhere from minutes to get a run to start, or it may take days if you want to use a very big chunk of the machine. The wall time, that's how long the run actually runs for, and when you submit a job, you have to say, this is how long I want my job to run for. It can run for less time, but that's sort of the maximum time. So wall time is an important concept in high-performance computing. Now, I mentioned earlier that storage and transfer rates and all this is very important. This relates in part to what type of storage we use. So this is something called latency, the time it takes data to be stored or retrieved, and so we want to consider latency when we actually start designing our systems. Non-volatile storage, this is the systems that even when you turn the power off, this is where it still stores the data. We have different types, and so in your desktop machine, this is commonly your hard disk. Okay, or we can use solid state drives, so the USB thumb drives that we have, those are solid state, there's no spinning parts. These happen to be super fast, right? So at the top we have the fastest devices, and at the bottom we have the slowest ones. Spinning disks, so this includes hard disks. These can be quite quick. They can be used in parallel file systems, and so the NCI happens to have a large number of spinning disks. And then magnetic tape, this is the slowest system, but it's also the most inexpensive. And so commonly there are big storage systems that can hold petabytes, so millions and millions of bytes. It's 10 to the 9th or something like that. And they commonly use a robot which will go out and grab an identified tape and then connect it to the system. So this takes time to access, but it's cost effective, and nowadays you can have 330 terabytes of data on a single cassette. GA has a tape robot down in the basement. So what is it about supercomputing projects? Why do we use supercomputers? Well, the projects that we do on a supercomputer tend to have one of these characteristics. They're either computationally intensive or they're data intensive. Computationally intensive, this is where we have a large number of calculations, and this requires having massively parallel design. So to do it efficiently, you will use tens of thousands of processors, run tens of thousands of simultaneous calculations, And so a big user of supercomputers is going to be climate models. They're very computationally intensive. Another option, and this is very common for GA projects, is where we have a large number of scenarios. So you may not have lots of individual calculations, but you want to run those calculations many, many times for different scenarios or different starting conditions, so input parameters. Then we also have data intensive. If it takes a long time to transfer data from one point to another, you can imagine that the further you have to transfer it, the longer it takes. So if you want to use lots of data and you want to have the lowest latency, you want to do your calculations where you're storing your data. So for big data, you're using large data sets, you want to do this in situ, and this is another use for supercomputer, and the NCI is specifically designed for this type of work. So that takes us to the NCI. The NCI, National Computational Infrastructure, it's located at the ANU, and this is their current supercomputer. It's the third or fourth, depending upon how you count these things. It's called Raijin, which corresponds for the Japanese thunder god. All computing centers seem to have some theme for their names, and the NCI has gods. The last one was Vayu, which is an Indian god. And when you look inside, that was all these different racks. The racks contain thousands of these circuit boards. Here we have that CPU unit, and then these are wired together using high-speed communication cables. And they've got tremendous air conditioning, etc. So you don't need to read the specifics. These are the stats for the NCI. As I said, it's located about 70 in the world. At 1.67 petaflops. Doesn't really make that much difference to GA because we don't really push this or use it to its extreme. Some of the key things, though, to keep in mind, it's got, let's call it 85,000 cores, and it's got GPUs. That's what this line is. But a really cool thing about it is that it's got these high-speed connections, and so these connections are about 1,000 times faster than what the NBN does. So when they talk about, why do you do this in situ? Why don't you transfer your data using the NBN? It's because this is 1,000 times faster having it stored locally. Okay? There's also a cloud over at the NCI. Tenjin. Tenjin is the Japanese god of sky, or sky god, thunder god, sky god. We've got a theme here. And then we also have research data collections over there, 10 petabytes, so lots of data, and Alex will talk about data and those things later. GA belongs to a partnership. This was set up back in 2010 when the infrastructure was originally set up, and this helps to pay for the operating costs of the NCI. Since we are a partner, we get to use a share of the resources, and so every year, we get to use about 3% of all of the processing hours and the storage and the help desk, et cetera, et cetera. The big partners are CSIRO and the Bureau of Meteorology and ANU, who's the host. And then an additional 20%, so 20% of the machine is made available to the general research community through a merit allocation scheme that anyone can submit applications to, proposals. So how does GA use the supercomputer? You can see that we started using the supercomputer, and so these circles, these pie charts, they're scaled based upon how much usage we've had over time. And then the colors, I've sort of broken this up to show the theme, so what types of work. And so we started off in 2010, primarily doing Earth observations and geothermal work. Over time, this has evolved somewhat, and you can see now that we are primarily, or our big users are Earth observations, geophysics, and hazards modeling. And all of those of you who were here last week for the seminar would have heard one of the examples of the hazards work over at the NCI. But we are expanding into other things, and hopefully we'll see some other projects becoming more and more involved at the NCI. So what are some examples? Well, we've got DEA. This involves data processing, so this is one of our primary usage of the NCI is data processing, and in this case it was to take a very large data collection, the Landsat archive, and make it accessible so that people can actually run analysis on it. The actual analysis generates products like WAFs. Here we have one of the maps of water over time. We also do geophysics. GA has been involved in the collection of large numbers of sample points or surveys around Australia, and then we do inversion, so we use that data to try and infer what's going on underground. We've done simulations of particle transport. This was Jonathan Kuhl's work, which encircles Australia. And we've done a lot in hazard space. This was the volcanic ash hazards assessment, which modeled the South Pacific and the impact of volcanic ash eruptions. So for those of you who are interested, anyone who's a GA staff member can join. We also have outside users joining GA projects. This is fairly straightforward. It's done through the NCI's Mancini system. It's self-service, and you can learn about this by going to the intranet page. We have a new reinvigorated intranet page for anyone who's been to the old one that was rather static and out of date. So you can get there through the GA scientific data team. And we've got new guidelines for GA users and project CIs. If you have any questions about training, talk to Grant Butler, who's our project coordinator. And also you can contact the NCI. They've got great user support and help desk. And with that, I'll pass it over to Alex.
G'day everyone. I'll be talking a bit about the data-specific aspects of high-performance computing, and we refer to that as high-performance data. Firstly, I'll talk a bit about big data. It's a term that's been thrown around a lot and perhaps overhyped, but I've heard quite a few definitions of it. One of the cute ones was anything bigger than what you can handle in Excel. There's also another one that has found its way into various literature and presentations where they talk about the V's. There's 4 V's that started with. I've seen as many as 42, and that just starts getting verbose and silly. But really the one I like is any data set too large to be dealt with using conventional technologies on a single computer. So nowadays parallel computing is becoming the norm for large problems. So, but big data is something that it would take you forever crunching through it on a single computer. An interesting point is that the NCI was actually one of the first data-centric scientific computing facilities set up in the world. I spoke to a few people from Europe and they were being offered compute from various facilities, but they'd go along and the compute facilities would say, oh, a terabyte, that's a lot of data, and we were happily playing with petabyte scale data at the NCI. So it's actually, it has been a point of difference with the NCI, but the other HPC facilities around the world have cottoned on, and now you're seeing more of these integrated facilities that are designed more for data-intensive computing. So how can we store our data in ways that support high-performance computing? People who are new to supercomputing picture they see the massive data centre at the NCI and they think that's a huge machine, you're just going to smash the problem. This isn't entirely true. As Dave pointed out with the nodes and cores, this is actually more like what you deal with. You actually have an army of cores, and so you need to be able to divide a very large piece of data up into small manageable pieces. As Dave mentioned, a node has multiple cores. Those cores can share memory, but the different nodes typically don't share anything. It's called shared nothing. And you need to get the data to the nodes in ways that the node can actually handle. So an alternate definition of HPC is a way of turning a compute problem into an input-output problem. So we've got oodles of compute at the NCI, more than we can use. But if you have a look at the stats for different projects, there's a ratio between the wall time or the elapsed time for jobs and the actual CPU time. And the ideal would be 100% CPU utilisation, but typically for GA applications which use a lot of data, the CPUs are actually sitting idle waiting for the data to come from the disk or be written to the disk. So I thought I'd better talk about structured versus unstructured data. The structured data has a very well-defined format. We know what the content is. Unstructured data is things like free-form text, social media content, images, video. Now, Earth observation data is often looked at as images, but it's actually very highly structured data because every pixel in Earth observation represents a patch of dirt. So all geoscientific data, or pretty much all geoscientific data is highly structured. So every data point has a specific relationship to every other data point. And that's very important because you hear a lot in the literature and presentations about these whiz-bang tools for big data. And it might be for doing things like word counts in documents where it doesn't matter how you divide up the task and you wind up with one number at the end. But with a lot of GA's data, the geospatial aspects are of great concern to us. We want to maintain the integrity of that data. So we need to prepare the data in a way that suits HPC. We also need to make sure that we can still manage the data. So if we were to pre-shard our data and turn it into a million tiny little tiles or something like that, it creates a management headache. It's very difficult to actually keep those organised. And as Dave mentioned, we need to actually locate the data where the compute is, ideally, for these very large data-intensive jobs. So we need to turn a single mass into many small, easily digestible pieces. And as I've mentioned, we need to take care of, to maintain the structural information as well. So one temptation is to just apply brute force, to use a relatively inefficient format like a text-based format or something like that and just throw the compute at it. To some extent that might hide your problem, but it's particularly important that we address the efficiency of the data storage in environments like AWS where you're actually paying to access the data, not just to store it. At the NCI, we have a storage allocation and there's additional storage allocated to data sets of national significance, but we don't pay to access that data. But you can make your processes a lot more efficient if you're clever about how you prepare the data. So I won't go through these point by point, but legacy data formats are typically formats that people are used to using. They were developed a few years ago for specialised desktop applications, and people are very fond of their legacy formats. But typically we find that they're not well suited to HPC environments. So these are some of the problems that we find with them. So the character-based ones in particular are very inefficient storage-wise, but they're more interoperable. People can see what's in them. But the very dense binary formats have the other problem. They're very hard to understand it unless you know exactly what's in them, but they're more efficient in terms of storage. And what we're aiming for is an environment that supports machine-to-machine interaction. So this is perhaps straying a little bit outside the pure HPC, but we have to look at these aspects when we're preparing our data. So The formats that we tend to gravitate towards, HDF5 is the hierarchical data format, and it's a generic container format for data, and you can do all sorts of weird and wonderful data structures in it. And we're starting to see more and more HDF5 based formats. There's a passive seismic one called ASDF. There's sorted pulse data, which is the full waveform data for LiDAR, and they all use HDF5 as the container format. The libraries are very good, well proven, but there are no constraints around how you can structure your data. So NetCDF4 applies some constraints around how you can structure your data in HDF, and also has some rules about what metadata needs to be in there and how that metadata needs to be presented. NetCDF CF, or climate and forecasting, is another level of constraint again. And the idea is that if you have a NetCDF CF, then applications will be able to read that straight out of the box. And that's important to the climate community because they share their research worldwide. So, as before, the disadvantages of the legacy formats, I won't go through every one of the benefits of these modern container formats, but these are some of the reasons why we're trying to actually translate the data. In translating the data to these new formats, we're also trying to maintain support for the legacy formats. So we make sure that the translations are lossless so that we can go to these new formats or back to the legacy ones as required to support existing workflows. So one of the specific benefits that HDF5 offers is chunking. Now, I mentioned before the need to actually break the data up into small pieces for parallel processing, and the management headaches that you can create if you pre-shard your data. By chunking the data up, the data is still very well organised, but it's held together in one storage unit. But we can access very small subsets, and you only need to read and decompress the chunks that actually contain the data you're interested in. So in many ways that allows us to have our cake and eat it too. Because a lot of the legacy formats are very difficult. It's very difficult to read small subsets out of them. You have to actually, there are computer science reasons involving contiguous storage and striding and so forth, but chunking works very, very well. So we move on to the boring but very essential stuff. How do we make the data useful, not just in an HPC context, but to people who don't have access to the NCI? As I mentioned there, HPC is only part of the picture. We need to make our data widely useful. So open data, you may have heard this term. Open data is the basic principle that if data is publicly funded, then it should be publicly available. It's government policy. So it's also government policy in the US. It creates a few practical issues for us preparing and presenting that data, but you can see some of the benefits mentioned there, and it's very much the direction that GA's moved in consistent with government policy. So I talked about metadata. We've got Andy Marshall in the audience there. Andy used to have a full head of hair before he started dealing with metadata. It means data about data. So it tells us where the data came from, who's responsible for it, what's being done to it. Basically, instead of just having a file containing the data, we have information about that data, and that's very, very important to make the data useful, because people who are experts in a particular data set, they know what's in it. But other people wanting to use that data will need to know things as basic as what unit it's stored in. So we assign digital object identifiers to data sets, and what these are used for is data citation. So when somebody uses the data and publishes a research paper or something like that, they cite the digital object identifier, and that DOI can actually be used as part of a URL to take you back to the metadata, and the metadata should tell you how to get that data. So it helps with reproducibility and good science. So web services, there's a move towards more web services. So instead of finding a file, downloading it to your PC and working on it on your PC, you access the data directly from its source, and you only access what you need. So you pull subsets, and the sorts of things that this allows, I mentioned a few web services there. Catalogue service for the web, that's used for machine-to-machine discovery, so you can actually go and look in GA's catalogue for certain data sets. Web mapping service allows, that's a very popular one in the geosciences. It allows you to actually visualise a spatial data set in something like ArcGIS or QGIS or something like that. Web coverage service is a way of accessing the data, and OpenDAP is another one that's come out of NASA and NOAA and people in the US. But these web services would allow you to do things like actually set something up in the public cloud on AWS that draws data from our data stores at the NCI. And if we didn't provide that kind of access, the data would be locked up in the NCI. So the web services are a very important part of what we do. So I'll mention the National Environmental Research Data Interoperability Platform, a bit of a mouthful there. The key thing about that is it's a layered architecture. You can see the simplified layer diagram there. The data storage infrastructure would be the parallel file system at the NCI. On top of that, we have the data in these standard formats, the modern container formats that support the data access services. And we then have applications like the Australian National Virtual Geophysics Lab and the Virtual Hazards Laboratory, and any number of applications accessing that data, not just from the NCI but also outside as well. And the cool thing is that you can actually plug into that layer wherever it suits you. If you're lucky enough to have NCI access, you can access the files directly on the file system, so there's as little between you and the data as possible. But if you only have access from outside, you can use one of the portals to do it. So I'll talk a bit about the FAIR data principles. This could be regarded as a restatement of some of our science principles, but it's a framework for preparing your open data so it maximises its value. So we want it to be findable, accessible, interoperable and reusable. So findable, I mentioned the catalogue, and it's very important that people can actually find data sets that they're after. So they can browse it manually, or they can do a machine-based search based on keywords or bounding boxes or a number of different attributes, and that's a very important thing, that people can actually find the metadata. I didn't mention originally when I was talking about metadata, our metadata is harvested by data.gov.au and the NCI, so they actually pull a copy of our metadata and cache it locally, so they make use of it in that way. So this is a little command line utility wrapper that I wrote to do CSW queries, so you don't have to compose the query in all its ugliness. And this is Ollie Raymond's AusGen portal, which actually uses CSW to find the data sets in not just our catalogue but some of the state catalogues as well, and it also accesses the data via web services. So that's an example of service-oriented architecture using web services. So accessible, the data should be available to people. Open data needs to be, people need to get at it. So if it's locked away at the NCI, it's of no good to anyone, even if they know it's on the NCI. If they don't have access to the NCI, that's it, end of story. So we need to make it available in a technical sense, but there's also licensing. There are reasons why we can't, not so much GA, but some data can't be made open. Medical data is a perfect example of that. There are confidentiality reasons around that. There's some data that GA deals with that's commercially sensitive, and things might be embargoed ahead of publication. So various reasons, but by and large, our significant data sets are made available under the Creative Commons by attribution license. So that means anyone can use it, but all you need to do is acknowledge where you got the data from. So interoperable, we adhere to standards. If we cook up some weird format or weird protocol that nobody else understands, and we have a very tightly coupled architecture, then that's no good. But if we can actually deliver these standards so that people can hook to them from their own applications as they require, then it really, the use of the data fans out. There's a lot more that people can do with the data. I'll mention linked data. This is part of interoperability, and basically that's using the World Wide Web like a gigantic database. So it means that you store references to data rather than trying to copy it all. So it means we can, say for example, link to a survey rather than copying all the survey data into the data sets, survey metadata into the data sets metadata. That's some work that Nick Carr has set us on the path of developing, and we hope to do a lot more in that area. And reusable. So we need to make sure that the data is not dumbed down at any stage, that we preserve its richness. We say how we arrived at the data, so the provenance, where it came from, what algorithms, software, all of those sorts of things. And I've mentioned the metadata. It's really important. One of the interesting things when I started working on the geophysics data, I think it took me 3 days to do the first translations, and it took me well over 6 months to get the metadata right. So that's an example of how grueling it is to get everything prepared. But once it's done, and it makes the data enormously useful being able to find it. So I mentioned the geophysical data. There's some 300 terabytes, and that's set to increase. There's the exploration for the future program. So all of the workflows that we've been developing for the legacy data sets, we've developed with an eye to the large amount of data that's going to be coming in. And we have the National Geophysics Data Collection as part of the research data services. So that's government-funded storage for data sets of national significance. And Dave's already mentioned the Digital Earth Australia program. They use NetCDF as the container format for the Earth observations. So, and they provide an API on the NCI to allow people to access that data. So I think that about covers our talk, and so by way of summary, Dave's talked about some different types of HPC. There's the cloud like AWS and supercomputing, and we're lucky enough to have access to the NCI. So that was one of the exciting things about coming to work at GA was the ability to actually work on some world-class infrastructure like we've got available to us at the NCI. So also the supercomputers are composed of thousands of cores, so that has a bearing on how you formulate the problem for parallel processing, and there's a fair bit of work that needs to go into that usually. The NCI's got 20 petabytes of high-speed storage, so the InfiniBand links, that's pretty awesome. That's one of the downsides with the public cloud. AWS have been addressing it and making more data available close to processing, but it's still a little bit expensive at this stage. And data needs to be carefully prepared for efficient HPC, and we need to make sure that we can manage it and that it's useful to the wider community. And the way we do that is by adhering to the FAIR principles. So thanks very much for listening.